Okay, so last time we talked about the main heat transfer processes in buildings, and we said that we have conduction, convection, radiation, and plus also energy storage and latent heat can play a major role in energy transfer in a building, and we'll introduce several strategies today. So the envelope is interacting with the surroundings through different modes. We have the solar gain, the heat exchange through the wall. We have some infiltration. We have inside the space internal generation and heat storage. Now, first, for conductive transfer, we know that conductive transfer is calculated by the following relation. So Q conduction in watt per meter Kelvin is minus K dt by dx. So whenever we put Q second in watt per meter square, it's equal to minus K dt by dx. And one very important property to know about conduction is the thermal conductivity K. So larger the thermal conductivity, larger the heat flux. So in general, for the envelope, we tend to select material with low conductivity in order to reduce the heat losses between the internal and the external space. And here we can see a range of materials with different conductivity, and we can then select based on our application which material to go for. Now, here we can summarize, if you want, the main properties affecting convection. If you want to calculate the flux in, if you want, in watt, just you have to multiply by the area. And we'll see together that we can give a general expression for flux, if it's conduction, convection, etc. And just we define what we call the U value. Okay, so as we have seen already, for conduction, Q second is minus K dt by dx. If we want to get Q, which is in meters, in watt, we multiply by meter square. So Q is a minus K times A, times the area, times dt by dx. And then if we consider a certain thickness, if you want, of the wall, we know that in case of pure conduction, the variation of temperature within the wall will be linear. So we can say that we take the absolute value of temperature change over the thickness. So we can say that in conduction, we can write K times A times delta T over the thickness. So again, delta T represents the absolute value of temperature change. So if you compare this expression with the general expression of heat exchange, which is UA delta T, you can define what we call a resistance due to conduction, a resistance of convection, etc. So if we compare both terms, we can say that the resistance can be calculated as the flux, phi, as delta T over phi, because if you take R to the other side, you get that the resistance is delta T over phi. And then if you apply this here, you can deduce that the resistance in conduction is equal to Ka is equal to delta T over Ka delta T over L. So L will go upward. And if we simplify delta T, we deduce that the resistance in conduction can be written as L over Ka, okay? So if we consider per unit area, it's, if you want, L over K. So from here, we can define the U value. The U value is the opposite to the resistance, as you can see here, because if we look at the definition, okay, R is 1 over UA. Okay, so R is 1 over UA. And now we have seen the expression of R in case of conduction. Okay, in case of conduction, R is equal to L over Ka. So from here, we can deduce what is the U value in conduction. A will be simplified, and the U value in conduction is K over L. Okay. So from here, we can say that in case of conduction, the main property is the thermal conductivity. In some books, they call it lambda or K. And we define the thermal resistivity as 1 over lambda or 1 over K. Now, concerning the U value, as we demonstrated here, is K over L. So larger is K, larger is U. So if you want to have good insulation properties, we should have small k and small u. And as expected, larger the thickness, lower will be the U value because we'll oppose heat transfer. So this is about conduction. Now, similarly, okay, for convection, we can define also a overall transfer coefficient U. So it is the same form, UA delta T, but in case of convection, the property is what we call the convective coefficient H. And the convective coefficient H is affected by several factors. It will be affected by the type of fluid going over the surface, the velocity of the fluid, etc. That's why, in general, H is defined in an empirical way, not by theory. So we do experiment and we give values for H. Now, if we compare this general expression, we can see that the U value in convection is equal to H, okay? While the resistance value is 1 over HA, because if we go back to the definition of resistance, which is delta T over the flux, so R convection will be equal to delta T over HA delta T. So delta T will cancel out. And we can see that the resistance in convection is 1 over HA. And here we can compare some values for H. And this comparison is very important for next chapter, which is energy efficient strategies to use in buildings. We'll rely a lot, okay, on natural and forced ventilation. Natural ventilation is limited to relatively low values of H because we don't have, let's say, a pump or a fan that will allow us to force, let's say, water or force air to move. Okay, so that's why H is relatively low, but it represents the advantage of being a simple mechanism and it doesn't require a lot of initial cost and operation cost. However, for forced convection, you should have continuously an external action that is forcing the fluid. It can be, as we discussed, we can use for air a fan, we can use, let's say, for water, we can use a pump, etc. So in this case, we have high values of H for gas, and for liquid much larger values. That's why whenever we want to cool, for example, a thermal engine, let's say, of course, we'll use a liquid rather than gas because of the high temperature we reach. So we need a more effective tool than we cool by water or we cool by a certain liquid. Now, in buildings, it's very important to be aware of infiltration. And of course, we should control it, but it should not be equal to zero because we always need to have some fresh air entering. We need to have some circulation. So it's in general, we recommend a certain fraction of infiltration, but it should not be very large, because if it's very large, it can increase a lot the ventilation loads. And to calculate the heat exchanged by infiltration, it's simply, if you want, you have a mass of air, a mass flux of air that is carrying heat. And we can calculate the heat carried as m dot Cp times delta T, where Cp represents the specific heat, m dot the mass flow rate, okay, and delta T the variation in temperature. So also we'll discuss in next chapter how to control such issues. Finally, we have the radiation. Okay, so also in buildings we have radiative heat transfer through through glazing, through windows, etc. And we should be aware that whenever we have a flux hitting a surface, we have this flux will be divided into several parts. And from here, we should appropriately select the type of glass we use. So first you have a certain fraction that will be reflected, another fraction that will be absorbed, and a third fraction that will be transmitted. Of course, if you have 100% transmitted, you might have a overheating of your space, okay? And in case, let's say during winter, you need in some places to have a certain fraction that is coming in, also you should not have it zero. So this should be studied. You should select a certain material that will give you the desired fractions. And the summation of fractions, alpha plus tau plus rho, where alpha will represent the absorbed fraction, tau will represent the transmitted fraction, and rho will represent the reflection fraction, should be equal to 1. Now, how to compute the total emitted flux by radiation from a surface? So whenever you have a surface and you want to determine the emitted flux by radiation, you can say it's equal to a certain property epsilon, which is a property of the material, epsilon, which is depending in general on the temperature, times sigma, which is the Boltzmann constant. This is a constant always given. And here it's 10 minus 8 times area times T to the power 4. So you can see that the radiation is proportional to T to the power 4. So larger the temperature of your surface, larger the radiative heat, and it's increasing in a very fast way. So if you increase the temperature, the radiation flux will increase considerably. So we should pay attention for radiation fluxes that can come from glass surfaces. Now, as we discussed in buildings, it's very important to know about heat storage and how it can take place, and to select the appropriate material, because as we discussed last time, we can have, especially in regions like Bekaa, we can have large variation in temperature between day and night. So during the day, we might have overheating, so we need to store energy. And during night, we have relatively low temperatures, so we need to release heat back. So a very good solution will be heat storage. And we should select a material that is able to store enough heat, okay, and release it during night. We have several possibilities that we'll discuss after. We can use phase change material. We can use a material with high specific with a high specific heat capacity, etc. Now, whenever we talk about heat storage, one possibility is phase transition. So, like when we say, for example, PCM, phase change material, the idea is the following. We have, let's say, we encapsulate inside, let's say, some solid barriers, okay? We encapsulate, let's say, a liquid, and this liquid can, when you heat it, or when you cool it, if you want, when you cool it, it will release heat, Okay, and when it will release heat, it will change phase from liquid to solid. And then when you have overheating inside your over your space, what will happen is that this solid now will absorb heat and will be transformed to liquid. So it can help you to dampen the variation of temperature in your environment, because when, let's say, the temperature is high, okay, it will take heat from you and it will change phase from solid to liquid. And then when the temperature is low inside your space, then what will happen is that it will release heat, okay, and then go from liquid to solid. So this is the phase change. It can be melting, freezing, as we discussed now, or vaporization, condensation, in case you go from liquid to gaseous state. Now, in case we are relying on heat storage by latent heat, we can compute the amount of heat stored by M, which is the total mass, times the latent heat coefficient. The latent heat coefficient is a property of the material you are using, okay? And the value of latent heat is in kilojoule per kilogram. For example, the latent heat of vaporization of water is of the order of 2,257 kilojoule per kilogram. That's why water constitute, if you want, a good option for heat storage. So in buildings, all of these heat transfer processes are taking place. In walls, you have convection, conduction, absorption of the sunlight, and heat storage. In glazing, you have at the surface of glazing, you have the convection process. Within the glazing material, you have conduction. You have also transmission of sunlight. And we can talk then about also let's say, the air and water tightness. You should pay attention you don't have leakages through the frame of glazing. In case of the roof, you should study also convection with the external environment, conduction through the thickness of the roof, absorption of sunlight, and water tightness. Now, the envelope is of high importance because through the envelope, you can have exchange of heat, water, and airflow by convection. And other transfer processes, you have the natural gas supply from the network, the electricity supply from the grid, the domestic water supply from the mains, and the heat supply from a district heating network. All of these are different energy and mass transfer involved in the envelope of our building. And that's why in the next chapter, we'll study the different energy efficient strategies that can be implemented to buildings in order to reduce the energy consumption and to make our space comfortable and healthy. Any question on this chapter? Okay. So now I will start with energy efficient strategies to be used in buildings. So what we want to do, we tend, as we discussed last time, to construct buildings that first can go from the state that is currently to the passive state. So we have defined some criteria to consider a building passive. So we reduced, if you want, the energy needs to a high extent, and we aim after to transform our building to be a positive building if possible, so to produce energy instead of consuming it. And here really will be the challenge, because this will affect a lot the economy of a country, because if all buildings, let's say, can produce energy, imagine the amount of energy we can save, the amount of fossil fuel use that we can reduce, etc. So first strategy that is widely used in passive building is the solar heating. So we should study solar energy, do the solar design, implement some solar strategies, study the landscape, and introduce active solar technologies. We know, so you know that solar energy is one of the main renewable energy categories, and it's widely used, and it's the future really is for solar, wind, hydropower, etc. And now solar energy constitute, if you want, the biggest percentage of renewable energy used in the world. This is because of uh, it's highly available. Plus, we have a lot of technologies that are developed that are using solar energy. So it is used for both new and retrofit projects. And as we discussed in this course, we'll tackle both. Okay. So we can build from zero. If we build it from zero, we have more challenges because we can take into consideration all factors that maybe we cannot play with in already existing buildings. So whenever you want to design a new building, you should pay attention for all of these criteria from A to Z. From first the selection of the appropriate orientation, the appropriate landscape. You should implement all possible strategies. And as we discussed, we need to do economical analysis because we have a lot of strategies, but maybe if you combine several ones working on the same aspect, you will increase the cost without increasing a lot the energy efficiency. So always we should do both economical analysis and engineering analysis for our building. And in case we are retrofitting a project, also we have other concerns. We have the architecture of the building that we should preserve. We have a lot of limitations because we cannot change the orientations. There is a lot of factors we cannot play with. So also we should select convenient strategies that can be implemented as much as possible to reduce the energy consumption. So solar energy can substantially enhance building design. Solar energy offers a lot of advantages over conventional energy. First, it's free after recovering upfront capital costs. So here, the importance always of economical analysis whenever we implement any renewable energy strategy, because mainly the problem of renewable energy technologies is really the initial investment. You have high initial investment, and you might need a large period to recover your capital. That's why whenever we suggest any project, we should do the economical analysis, especially if you have renewable energy because of the large initial investment. So we should make sure that the payback time period can be relatively short and to be able to have an economically viable system. This is why, as we discussed, we developed a lot solar technologies to make them economically viable and to have relatively acceptable payback periods. So solar energy is available everywhere and it's inexhaustible. So this is one of the biggest advantage. And of course, in some countries, it is available less than others, but in general, in the majority of country, we have some sunny hours. It's a clean, so for the environment also, it's very important because it's a clean strategy, reducing demand for fossil fuels and hydroelectricity and their environmental drawbacks, and can be building integrated, which can reduce energy distribution and needs. One big advantage of solar energy is that it can be easily integrated to retrofit projects. And this is what we are doing in Lebanon now. The majority of existing buildings were able to install solar energy and to use it. Now, whenever we study solar energy, we should know just some properties about the sun. So the sun emits energy as electromagnetic radiation, and it's equivalent to the energy of 5,725 degrees Fahrenheit. So imagine the high amount of energy delivered. And it's equal to 36,000 times the amount of energy currently provided by total world oil consumption per year. So if we can benefit from this energy, we can really avoid using any fossil fuels or oil or anything, because it is widely available, but what is missing is the tools to use it. So the amount of energy that reaches Earth's upper atmosphere is nearly 1,350 watt per meter square, which is called the solar constant. In Canada, the peak solar intensity varies from about 900 watt per meter square to 1,050 watt per meter square, depending on sky conditions. So you know that Canada is one of the cold countries, and even for this cold country, we have a considerable amount of solar energy. Peak solar intensity is at solar noon when the sun is due south. So also we can work on orientation if you want of our systems. We have a lot of strategies that will track the sun, okay, and this will allow us to benefit to maximum from solar energy. Plus, in addition to all of this, the sun is the source of all energy available on Earth directly or indirectly, including fossil fuels. So all other energies are related to the sun because we'll see after, for example, let's say when we talk about wind, okay, wind is mainly affected by velocity of wind, and the velocity of wind is related to the sun. And I will not go over the details of this, but we have a relation between solar energy and all types of nearly of energy through, let's say, wind for biomass. You know the direct relation. So trees need solar energy to be able to grow up. Let's say for fossil fuel, you know that the formation of fossil fuel is under high pressure and temperature, so also we need the sun, etc. So the sun is affecting all energy available on Earth. Energy from the sun can reach the Earth in different ways as direct, reflected, and diffuse radiation. So, whenever we talk about direct, so as the name indicates, whenever you have the solar flux that is transmitted from the atmosphere to the Earth, this is the direct one. The reflected one, we discussed together already greenhouse gas effects. Okay, we said that when greenhouse gases are trapped by the atmosphere, if we have a high percentage trapped, this will lead to reflective properties. Okay, and whenever then you have emission from the Earth, a part will be reflected back to the Earth. Okay, so that's why we can have energy reaching the Earth as direct, reflected, and also diffuse radiation. Whenever we talk about diffuse radiation, you have, whenever you have, let's say, a cloudy day, it's true that you will not have direct, maybe because of the cloud cover, the energy will not be transmitted directly, but because of diffusion, okay, heat will be transmitted in a diffusive way. So direct radiation is the highest on a surface perpendicular to the sun rays, and the angle of incidence in this case will be 0 degrees. And of course, this will provide the most usable heat, but also diffuse radiation is the energy from the sun that is scattered within the atmosphere by clouds, dust, or pollution and becomes non-directional. On a cloudy day, 100% of the energy may be diffuse radiation, and on a sunny day, less than 20% may be diffuse. So the amount of the sun's energy reaching the surface of the Earth will also depend on the cloud cover, the air pollution, the location, and the time of the year. And of course, whenever we study solar energy, we should study the climate of the country in order to determine the variation with year of solar energy received in its different forms. Now, whenever we talk about solar systems, okay, we can first, if you want, categorize several parts, and we can talk about three main steps to use the energy of the sun, which is the collection step, the storage step, and the distribution step. Okay. And also will differentiate between passive, if you want, techniques and active techniques. So a passive solar building will not require, if you want, any equipment that needs, let's say, external energy. And for example, if you need to circulate water through a pump, you consider that I need a pump that should be that needs electricity to be driven. Okay, so whenever we talk about completely passive system, you don't need any external power to be given to the system. This can be done, for example, by relying on natural convection, for example. So we'll take a lot of examples in this session. So natural energy flows through air and materials as radiation, conduction, absorption, and natural convection. So whenever, let's say, you have a window, okay, heat will come to your space, and you don't need to operate, if you want, any active system. So here you can consider, you just have the initial investment when you select the material of your window in a way to let enter the percentage that you want. And after this, flow of energy will come in a natural way by the main heat processes that we discussed, as radiation, conduction, natural convection. If we talk also about, for example, free convection or natural convection, whenever you create temperature density difference or temperature difference, you will have flow of air by natural convection due to difference in buoyancy, and this will lead like to natural ventilation of your space. So as I mentioned, we'll discuss these strategies in coming slides. So windows are the collectors, and interior materials will be the heat storage media. That's why we should appropriately select the interior materials, depending, of course, on the climate, depending on, let's say, the season. Of course, for the season, you have your house, you should select a material that can work for any season. So it depends mainly, if you want, on the country, to select the materials that should be used. And plus, sometimes what we do, from one room to the other, we can, let's say, add some layers of materials, because you have some regions, let's say, that are directly exposed to the sun more than other regions. So in these regions, you can use specific materials in order to increase the heat storage capacity. Other passive solar systems are water or air solar heaters that use natural convection or thermosiphon effect for heat storage without needing pumps or fans. Now, the advantage of passive technologies is if you want, the reduction in energy bills, because you don't need to have an external supply, let's say, of electricity. But also, the amount of ventilation, if you want, produced will not be as large as mechanical system. So that's why also another strategy, let's say you have a very high uh, load to remove, you might go to mechanical or active systems. But even here, even you are using mechanical equipment, the amount of electricity you are supplying to it is really small. Why? Because it will rely on mainly on the energy of the sun. So for example, an active solar system can use mechanical equipment just for operation, to collect, store, and distribute the sun's heat. But at the end, you will use sun's heat. So active system will consist, for example, of solar collectors as storage medium and a distribution system. Active solar systems are commonly used for water heating, space conditioning, production of electricity, and processing of heat. We'll take a lot of examples in the coming slides. Another strategy that can always be effective is hybrid power plants. It's very good in general to combine several systems of energy, because as we discussed last time, for example, if you combined wind and solar, this can be very interesting, because in some periods you have less hours of sun, but you have more wind. And on the other hand, whenever you have a high number of sun hours, you might have lower wind. So by combining strategies, you can increase the efficiency of the system, because it can work for nearly it can be independent for majority of times. to not have to rely and have backup of a fuel system. Now, whenever we want to do a solar design, okay, so the key aspects will be to go over several design parameters. So, of course, first we should tackle the location and orientation of the building. Of course, if we are building from zero. Like, if we are introducing a system also, if you are implementing or retrofitting, also you can study the already available orientation of the building in order to select the appropriate location to implement your solar system. We should study the fenestration area and the orientation and type. We should know the thermal massing and envelope characteristics. So as we discussed, for example, if you have a zone largely exposed to the sun, okay, in this zone, you should have thermal mass. So already implementing thermal mass will depend on the location of the room. If this room is exposed a lot to sun or not. So if you have some regions with lower exposure, you can select other thermal mass systems to be used. The amount of installations that we have, you can include shading devices. So sometimes to know if you need shading devices, in which locations, what is the type, location, and area needed. For effective thermal storage, insulated from the exterior environment, as well as the amount and type needed. So we should study all of these aspects to know which strategies to implement and in which locations. For example, okay, sometimes already I discussed with you thermal storage using latent heat, but you also, okay, can use the concept of sensible heat because, for example, concrete, when you use concrete in the building envelope with exterior installation, concrete is characterized by a high capacity of storing heat. Okay, so it can store heat in sensible form. So whenever the specific heat of a certain material is large, even if you heat by sensible heat, its temperature will not vary a lot because you know that Q sensible is equal to the mass of the storing material times its specific heat, Cp, times delta T. Okay? So if you have a very large value of specific heat and large mass, even if it store large amount, delta T will be relatively small. And this will allow to store heat without overheating surfaces. Okay? Yeah, I will continue in next session.